So in this video, we can look at Newton's third law and conservation of momentum in explosions. I've divided this video into chapters so you can skip through to the chapter you need. In the first chapter, we're going to look at what Newton's third law is. In the second chapter, I'll give you a short exercise applying Newton's third law to different contexts. Chapter 3 will look at a very quick experiment to prove conservation of momentum in explosions and analyse the results. In Chapter 4, I'll give you an example question of how to apply conservation of momentum in explosions. And then Chapter 5, you've got a set of questions on explosions that you can answer, and then I'll talk you through my worked answers afterwards. And finally, don't forget, there are two other videos linked to this one. The first one's conservation of momentum in collisions, which you should look at first. And then there's a video on exam question practice with worked answers on both collisions and explosions. So what's Newton's third law of motion? Well, first of all, Newton said when body A exerts a force on body B will exert an equal and opposite force on body A. So let's have a look. If body A exerts a force onto body B, then we're told that body B will exert an equal and opposite force on body A. Notice we can represent the size of the forces by either the length of the arrows or the width of the arrows, and they're both identical. And what that says is, for the third law, it will say that body A will be pushed backwards. And if body A goes backwards, because body B is being pushed as well, they will both move in opposite directions. So again, let's have a look. If we've got two skateboarders, skateboarder A pushes on skateboarder B, therefore this results in a second force where skateboard B applies force to skateboarder A, and therefore they're equal but opposite. And although A is the only one pushing, they will both exert a force on each other and they'll move apart. So Newton's third law is when you apply a force to an object, the object applies an equal but opposite force to you. And that's often called a paired interactive force because they're paired and they involve an interaction between the two objects. So pause the video and think what you'd put in each of those spaces using the keywords below. So we have, for every force there is an equal and opposite interaction. Forces always come in pairs called interaction pairs or interactive pairs. The interaction pair are the same type of force, so you can't have gravity acting with magnetism. The forces are the same in size but opposite in direction, and the forces act on different bodies. One force on the first body, the other force on the second. So this slide shows you 4 different interactive pairs of forces, 4 different applications of Newton's third law. Again, I've made sure that you're repeating the language over and over again to learn it. So read through this slide and decide what words you'll put in each one of these, and I'll go through them in a minute. Pause the video and have a go. So of course we have when two objects interact, the forces they exert on each other are equal in size but opposite in direction. So the first one is the girl pushing on the wall, and the wall applies an equal but opposite force, causing her to accelerate forwards. So I don't know if you've had experience of getting off a boat, but if you try and get off a boat without somebody holding on to it, you'll find the boat goes backwards and the gap between you and the pier gets larger. Now this is because in order for you to move forwards, you have to apply a force to the boat backwards, so the boat pushes you forwards. So the man pushes back on the boat, so the boat applies an equal but opposite force forwards, and that's the force that allows you to get off the boat. So when a book is on the top of the table, the book's weight pushes down on the table, so it's pushing on the table. this means the table applies an upward force on the book, which is equal but opposite. And of course, that's called your normal contact force. Normal because it's at right angles to the surface. So it's your normal contact force. And finally, how on earth do rockets work? Well, first of all, the rocket will push gas out backwards. And of course, that applies a force, so the rocket applies a force to the gas backwards, which means the gas applies an equal but opposite force, making the rocket accelerate forwards. So those are 4 examples of Newton's third law. So this is a lovely example of Newton's third law. If you watch the video, you will see, first of all, you've got the cannonball there in the cannon, and then there's an explosion which fires the cannonball forwards. Watch what happens to the cannon.
Fire in the hole!
So you can clearly see in slow motion, as a cannonball is fired forwards, the cannon recoils backwards. Of course, the cannon has to move backwards because the cannon applies a force to the cannonball, accelerating it forwards, which means the cannonball applies a force to the cannon, moving it backwards. And if you've ever been onto old ships where they have cannons in them, they have blocks underneath the cannon wheels at the back to stop them from moving backwards and hitting the person that's loaded the cannon. So let's now have a quick look at how we can prove that momentum is conserved in explosions. I've got a frictionless trolley system again here, and each of those weighs 1 kilogram. We have in here, you can't see it because it's hidden, is a loaded spring. And what you'll see in the video is I've got to tap this button here, and I've got to tap it without really applying a force that way to this cart. So I have to tap it, and eventually when I hit that exactly, the spring will unload and that will cause an explosion. This cart will go that way, and you've got the light gate here, and this interrupt card goes through that light gate, so it measures the speed of this cart going that way, and you've got this interrupt card on this vehicle which will allow this light gate to measure the speed of this vehicle in the opposite direction. And we should find the momentums are identical because the total momentum beforehand is 0, which means the total momentum afterwards must be 0. So watch this video quickly and then we'll look at some data. So within an experimental error, you saw that the carts came off at the same speed, but in opposite directions. So that means that the momentum is also conserved because the momentum of both are identical, but in opposite directions. So looking at that practical, you could see that if you've got identical carts, and these weigh 0.5 kilograms, but if you've got identical masses of carts and there's an explosion, then they come away with identical speeds, but in opposite directions. So one has a positive velocity and one has a negative velocity. And of course, therefore, the momentum is identical because it's mass times velocity. So the momentum of this cart is identical to this cart, but in the opposite direction. So one is positive and one is negative. If you add them together, they cancel each other out. So what happens if you add an extra mass to this? So we've made this 1 kilogram. Well, of course, the momentum before 0, the momentum afterwards must still be 0 in total. So the magnitude of this momentum must cancel out the magnitude of this momentum. And because this has got double the mass, it will come away with half the speed. So the momentum in magnitude is the same as the momentum of this cart. And finally, suppose we added even more mass to this to make that 2 kilograms and that 0.5 kilograms. Then of course, this will come away with a velocity a quarter of this because this has got 4 times the mass. So when you explain why objects move apart in explosions, there are two different approaches that you can use, and you have to be very careful in your exam which approach you are asked to do. It might say, explain why these two skateboarders move apart using Newton's third law, or it might say, explain why these skateboarders move apart using the idea of momentum. Or it might just say, explain why these two skateboarders move apart, and you could use either. But most of the time it explicitly states which approach it wants you to take, because it's testing you understand both of them. So pause the video, think what you'd write to explain it with Newton's third law, and then fill in the gaps yourself to see how you'd explain it using conservation of momentum. So using Newton's third law, we can say person A applies a force to person B. So Newton's second law says that person B will apply an equal but opposite force to person A. So they both move in opposite directions. 3 marks. So the second way of explaining it is using the idea of momentum. So we can say momentum before an explosion must equal 0 as the objects are stationary. The momentum after the collision must also be 0 due to conservation of momentum. This means objects travel in opposite directions, one having a positive momentum, the other having a negative momentum, so they cancel each other out. So let's now do some mathematics and apply conservation of momentum to a calculation. Don't ask me why I chose a rhino and a pig ice skating, but I thought it was a funny example. So the rhino and pig are going to push apart from each other, and that is like an explosion. And we're told the pig moves away with a speed of 10 meters a second and has a mass of 800 kilograms. I put this on ice because remember, conservation of momentum in explosion is only if external forces don't act. So it is a closed system. So strictly speaking, we shouldn't have any friction for these calculations to be right. And the rhino has a mass of 1,200 kilograms. So of course the rhino should come away with a lower speed than the pig. That's one way when you get your answer to have a think. Now I'm going to show you the way that you could argue it, and then a much easier way to argue it. So first of all, momentum is mass times velocity. And we know the total momentum has got to be 0. So we can add the two momentums together and they should be 0. So the momentum of the pig will be the pig's mass times the speed. And of course, because this momentum is in the opposite direction, it is negative. So we're adding a negative momentum. And the momentum of the rhino will be the rhino's mass times the rhino's speed, and adding those two together will equal 0. Now I think that's quite a difficult equation to then find V. So that is not the approach that I would take. I would take this approach instead. First of all, tell the examiner the total momentum is 0. Next, you can then argue that if the total momentum is 0, the magnitude of the momentum of the pig will equal the magnitude of the momentum of the rhino. So the momentum of the pig was mass times velocity, and that's got to equal in magnitude the mass of the rhino times the velocity of the rhino. And that's a much easier equation to rearrange. So we've got 8,000 is the momentum of the pig, and that's got to equal the magnitude of the momentum of the rhino. And now it's much easier to get V, the substitute equation. You just have to divide by 1,200, and that gives you 6.7 meters per second. So that's a much easier approach than doing that. So what you want to do is pause the video, have a go at those questions. If you get stuck on the first or second one and need more support, just forward the video to where I go through the worked answers and then go back and have a go at the others. So in the first question, momentum of the cannon in the magnitude equals momentum of the cannonball. So we don't know the momentum of the cannon, but we know 300 times the velocity is equal to the momentum of the cannonball, which is 5 times 50, which is 250. So therefore, the velocity of the cannon is going to be 250 divided by 300, which gives us 0.83. A different approach you could do is this. You could first work out the momentum of the cannonball, which is 250. You can then say the momentum of the cannon will be 250, which is equal to its mass times its velocity, and then do the same thing. So you can use either approach to do the question. Strictly speaking, this velocity is the velocity of the cannon, which is in the opposite direction of velocity of the ball. So when you quote your answer, you should really put minus 0.83 meters per second to show the direction. Question 2. I'm going to use the second approach. The momentum of the bullet, first of all, is mass times velocity, and the momentum of the bullet was 15. So therefore the momentum of the gun must be the same, but in the opposite direction, but we're just working out the magnitude. So it will be 15, which will equal its mass, 0.5, times its velocity. So therefore dividing 15 by 0.5, you get a velocity of 30. Again, you could have done it the other way by showing the momentum of the gun is equal to the momentum of the bullet. And so you've got 0.5 times the velocity is equal to 0.05 times 300. So exactly the same idea. Remember again, I haven't in my video written minus 30 meters per second, but strictly speaking, the velocity is minus 30 meters per second compared with the bullet. So first of all, on this one, I'm going to work out the momentum of the bullet because I know the mass and the velocity, which works out as 25. And so the momentum of the gun must also equal 25 in magnitude. So that's going to equal its mass, 3 times the velocity we don't know. So dividing 25 by 3 makes velocity the subject of the equation, and we get 8.3 meters a second. Again, strictly speaking, when you quote your answer, you could quote minus 8.3 meters a second because to show it's in the opposite direction to the velocity of the bullet. So in this one, the momentum of the cannonball is mass times velocity, which gives us 1,000 kilogram meters a second. So again, the momentum of the cannon must have the same momentum, but in opposite directions. So the magnitude will be the same, 1,000, and that will be equal to the mass of the cannon times the speed which it recoils, which is 2. Therefore, to make mass subject to the equation, it will be 1,000 divided by 2, which is 500 kilograms. So in the final question, this one is a classic because it's quite often asked in exam questions. If someone is on ice and they want to move this way, they have to throw something the other way to apply a force to the object, so it applies an equal force backwards. So if the boy throws a heavy enough bag, the boy will move backwards. So I've done this the other way. So the momentum of the boy equals the momentum of the ball, which means the momentum of the boy is mass times its velocity will be equal to the momentum of the ball, which is 2 times 2.5, which is 5. So therefore, the velocity of the boy is going to be 5 divided by 50 is 0.1. Again, if you quote the velocity as minus 0.1 meters a second, because the boy moves in the opposite direction to the ball, which has a positive velocity. Notice the boy is going to not move very fast backwards compared with the ball thrown forwards, because of course the mass of the boy is 50 times greater, so that should be 50 times less. So finally, do go on and do exam question practice with worked examples on collisions and explosions on my next video to be really secure at applying both conservation of momentum in collisions and explosions, 2 exam questions, and explaining why it happens using Newton's third law.